Self-cleaning ceramic tiles produced via stable coating of titanium dioxide nanoparticles.
Problem statement is to determine the advantages of photochromatic power of titanium dioxide. Second is to determine two strategies to coat ceramic tiles with titanium dioxide. And the third one is to measure photochromatic power of titanium dioxide. Coating surface with titanium dioxide and characteristic of titanium dioxide with high photochromatic power helps in self-cleaning properties and decomposition of pollutant. Two methods that being used is simple heat treatment and up-test method, which is coating tile with titanium dioxide particle. The second method is titanium dioxide nanoparticle is aminocyanalized using up-test treatment and then followed by their covalently attachment onto carbon monoxide plasma and treated with ceramic tile via EDC and NHS chemistry. It's then monitored by using dynamic light scattering DLS and X-ray photoelectron spectroscopy XPS.
So this is how the proposal works. We want to see how different approaches of covalent coating of titanium dioxide nanoparticles onto ceramic tiles to induce self-cleaning capability. Basically, there were two strategies that were introduced. The first one is a single heat treatment step. It is used to make a strong physical bond between the titanium dioxide particles and ceramic particles. The next one is we use APTES treatment technique to functionalize dioxide particles, and then the particles were covalently bonded to carbon dioxide plasma treated ceramic tile. So the question is, which strategies that can create a stable covalent coating of titanium dioxide nanoparticles onto ceramic tiles to induce self-cleaning? For the literature review of this journal is, with self-cleaning tiles, dirt is easier to remove from the surfaces without using aggressive detergents. So basically, the self-cleaning property allows to maintain unchanged the texture and appearances of the ceramic coatings. And rain is able to remove the dirt and clean the surfaces. It is a good technique as we no longer require the traditional external materials, which are more expensive and generally more toxic.
Methodology, it has 5 stages, which are dye degradation measurement of titanium dioxide nanoparticles, coating titanium dioxide nanoparticles using heat treatment technique, APTES treatment technique, and characterization technique. Coating titanium dioxide nanoparticles using heat treatment technique. First, add 30 microliter of 1 mg per 1 ml titanium dioxide nanoparticle suspension onto the ceramic tile surfaces and spread to cover the whole surface using a simple pipetting system, then left to dry at room temperature. Place the surfaces in a tube furnace or a vacuum oven for lower temperature. The heat treatment are done in different duration and at different temperature. Then rinse and wipe the surface to remove any unattached particle. Add 5 microliter of 1 mg per 1 ml of dye onto each surface and place in a UV chamber. APTES treatment technique. Homogenize titanium dioxide to nanoparticles with trimethylamine and ethanol at 60 degrees Celsius. Add ammonium hydroxide, deionized water, and APTES 1% to the suspension and left to stir overnight. Centrifuge the suspension at 4500 rpm for 15 minutes. Discard the supernatant and mix the pellet with ethanol. Repeat washing steps 3 times and store the powder in 50 ml of toluene. Then treat the clean surface of CO2 plasma and use EDC NHS ratio 1:1 to activate the carboxylic groups on the surface. Rinse the surface with deionized water and add the APTES treated titanium dioxide suspension to the surfaces and left for 2 hours. rinse the surfaces with deionized water and dry at room temperature. Add 5 microliter of 1 mg per 1 ml dye to the surfaces and left to dry. Place the surfaces in the UV chamber and image at different time intervals.
So this is the result for the heat treatment technique. If the temperature above anodized rutile phase, the photocatalytic activity of titanium dioxide particles could have deteriorated. As an alternative, the temperature was set below anodized rutile phase. As a result, 5 hours heat treatment at 200 degrees Celsius provided the best dye degradation properties for ceramic dyes. This is the result of the ceramic dyes coated with the APTS treatment method. After APTS treated particle is used, the dye was visible after 24 hours. To conclude, the rate of dye degradation using heat treatment is higher than using APTES treatment.